Consider a data set which represents the number of hours of TV watched by an elementary school class. Draw a histogram, oh my, and find the mean and median of the data set. So every data value here represents a student. So I'm using the same numbers on the axes. I went up to 7 for the x-axis though. But what do the numbers on the x-axis represent? Number of hours watched. And the y-axis represents, now say it, number of students is the y-axis. Can't see what I'm writing. Whatever the data is actually, whatever the data actually is the x-axis. And the number of those times is the y-axis. So remember, the y-axis is the frequency or your relative frequency. Is it okay? In this case, since it just says histogram, we're doing a frequency histogram. If there were a relative frequency, we'd have to find the probability that a student watched 1 hour, 2 hours, 3 hours. Okay? So now we count how many students watched 1 hour of television. 2. So the box for 1 goes up to 2. How many students have watched 2 hours of television? 3. 3 hours? 6. Oh gosh. 4 hours? 5, 6, 7 are all 1. What are we missing? A title. Well, that's just this. Number of hours of TV watched by an elementary school class. I'm just going to put it there. Title. So there be our histogram. If you would, please find the mean and the median for the data set. What I have for the mean up here, 1 plus 1 plus 2 plus 2 plus 2 plus ... plus 5 plus 6 plus 7, that's acceptable on your test. I'll allow it. I know there's a bunch of numbers there. But if you did 1 plus ... 7, come on, really? That's way too lazy. Don't be too lazy. We have 17 total kids in the class, so assuming those are all the kids, notice I put the population mean, the mu there. Mu. What is our population mean? Let's go 2 decimal places because it's not pretty. I got 3.29. Yeah. So if you had to interpret this, this means that on average, the kids in this class watch 3.29 hours of TV. Is this per day? Oh my gosh. That's a lot of TV. All right. As for the median, we have 17 values, which means we will have a median right from the set. So we're going to go in by 9 from either end. So which one is the 9th one? 3. 1, 2, 3, 4, 5, 6, 7, 8, 9. This 3. So notice for our data, our mean, 3.29, is bigger than our median, 3. when your mean is bigger than the median, we say the data is skewed right. Skewed, S-K-E-W-E-D. So we're going to define skew. But before we do, real quick, so here's the median, and 3.29 on the number line is about right here. There's the mean. Visually speaking, but this is not always going to work depending on the data, so that's why you want to look at the numbers. For certain sets of data, you can look at where the tail is at, so where it starts to flatten out. The side of the tail is on is how it's skewed. But it's not always going to work. So for instance, if your data, oh gosh, does something crazy like this, call a doctor, one, but two, it's very hard to see where the tail is at. You have to go by the definition of mean and median and how they interact with each other. I saw a hand. Yes. Oh, the tick marks? Yeah. I got to think. I wonder if I switch that from, where do we put the ones for the bar graph? We put them in the center. Oh, this is not a bar graph. This is a histogram. No, it's fine. Here's the deal. Let me put this down. I don't really care. As long as it's there. Yeah, I think you're right. It should say 1 here, 2 here.